Here we're going to look at probabilities and the sampling distribution of sample means. We'll be applying the central limit theorem to our sampling distributions. So the example I give you, suppose the GPA of all students at a college are normally distributed with a mean of mu equals 2.3 and a standard deviation of sigma equals 0.4. Let random variable x represent the GPA of a student. And we want to find the probability that x is less than 3. Okay, now this is something that we've actually already done in a previous lesson. So if you need to go back and review normal probabilities, so go back to the normal curve and normal distributions and look at the probability videos, okay, this is how you do it. So I'm going to go through this rather quickly. So what we look at is on a diagram, we have a random variable x. We know that 2.3 is right in the center because that's the mean. 3.0 is going to be to the right of that. Okay, so what we want to find is the probability that x is less than 3.0. So less than 3.0 means we're shading to the left. So that's why I have it shaded to the left here. So what we need to do to find probabilities is to convert x to z and then find probability. So we turn x into a z and then we find probability. So that what always relates x and probability is your z-score formula, x minus mu over sigma. So to do that, we take our x value of 3 minus the mean, 2.3, divided by the standard deviation of 0.4, and we get a z-score of 1.75. So that's where this is coming from here. People can do this differently, and I will even change it up as I go through different topics. You look at your random variable x, the mean was 2.3, and we're looking at x being less than 3.0, so that's on the x-axis. Well, what we're doing now is we're converting x into z. So when we convert 3.0 into a z-score, we get 1.75. And remember, 2.3 has a z-score of 0 because it's 0 standard deviations from the mean. Okay, so we have our x and z-axis. If you just want to use a z-axis, that's fine. Okay, I just show these to show the relationship between the two. And then we got to find probability. So that is where you take the probability that x is less than 3.0 equals the probability that z is less than 1.75. So this is where you go to your tables. Okay, 1.75. Okay, is right about here. So you get 0.9599. And if you use your calculator, you can use the normal CDF function, which I showed you in previous videos. Okay, so the probability that x is less than 3. So if you randomly choose a student, the probability that their GPA is less than 3.0 is almost 96%. Okay, so 0.9599. Okay, now what is different is now we want to find the probability that x bar is less than 3.0 with n equals 2. So now what we're saying is, if we take samples of size 2 and calculate x bar, the sample mean, we want to find the probability that the sample mean, is less than 3.0. So you have to look at how those are written. Probability x is less than 3, and here we have probability x bar is less than 3. The first one is saying the probability that one student has a GPA of less than 3. And down here we're saying what is the probability that a sample mean of 2 students has a GPA less than 3 on average. Okay, so now that we're looking at an x bar value, now we have to look at a sampling distribution of sample means, an SDSM. Okay, so the way that we find our SDSM, the mean of the sample means is equal to the mean of the original So 2.3 is in the center. We know that the x bar distribution, notice I have x bar now instead of x, that distribution is going to be normally distributed because the central limit theorem says if we start with a normal, okay, so we start with a normal, okay, so the x distribution is normal, we're going to end with the normal, no matter what your sample size is. So we know we have a normal distribution for the x bar. The standard deviation of the x bar distribution is now sigma over the square root of n, so 0.4 over the square root of 2. And that gave us approximately 0.28. So if we take our z formula now, instead of x minus mu over sigma, now we're dealing with the SDSM, so now it's x bar. Basically everything turns into x bars. X bar minus mu sub x bar over sigma sub x bar. So 3, notice that's coming from the parentheses, 3, minus the mean, 2.3, divided by sigma sub x bar, which is 0.4 over the square root of 2. Now what I'm going to tell you is, even though I rounded that to 0.28, I want you to put 0.4 over the square root of 2 in your calculator just to avoid any rounding errors. The only reason I would say 0.28 here is if you wanted to label it on an axis somewhere, you have to round it eventually. So that's why I rounded to 0.28 there. But when you're actually finding the z-score, do not round it. Okay, put 4 over the square root of 2 in. Okay, so the way you want to do this on your calculator, I'm going to show you this one. If we do 3 minus 2.3, we have to keep that together. So my suggestion is 3 minus 2.3, and then press enter. So that's 0.7, and you can do that in your head too. And then we're going to divide that by, we need to keep 0.4 over the square root of 2 all together. So you're going to put parentheses around 0.4, divide by square root of 2. Now notice when I press square root, parentheses pop up on my calculator. That may not happen on yours, but if it does, you have to end the square root part with the parenthesis, and then another parenthesis to close the first one. So that'll keep the 0.4 and the square root of 2 together. And you get 2.4748. So if you round to the nearest hundredth, because it's a z-score, we're going to round to the nearest hundredth, that's 2.47. Okay, so that's coming from right here. So the probability that x bar is less than 3 is now the probability that z is less than 2.47. And again, now just go to your table, look it up, and you get 0.9932, and you can use the normal CDF function on your calculator also. Now I'm going to point out that those decimals might be a tad off from the table because I use my calculator function to get those, but it should be extremely close either way. Okay, and then the next one, number 3. Now we're going to use n equals 25. So the same probability that the sample mean is less than 3, but now we have a larger sample size. So now they're saying if you're to take samples of size 25, what is the probability that a sample mean is less than 3? Well, remember, when the sample size gets larger, the SDSM gets more narrow. So when you draw this diagram, the x bar, or the mean of the x bar distribution, is still 2.3, but now the standard deviation is 0.08, which is 0.4 over the square root of 25. So now that distribution is much more narrow. So now when you put the 3.0 on the x bar axis and turn that into a z-score, so using that same formula again, z equals x bar minus mu sub x bar divided by sigma sub x bar. Notice the calculations are all very similar, except now we're dividing by 0.4 over the square root of 25. So because our sigma sub x bar is a smaller number, our answer is going to be larger now when you divide. So now we're dividing 0.7 by a smaller number, makes our answer larger. So now that sample mean of 3.0 is 8.75 standard deviations above the mean in this X bar distribution. So when you look up 8.75, okay, what you'll see is our distribution only goes to 3.49 all the way at the end here is 0.9998. Now I put 0.9999 because in the calculator when you do it, that it actually gives you 1 in the calculator. Okay, but I just put 0.9999. Okay, because there is more area out here, but it's very, very small. And now I rounded to 4 decimal places. Okay, so we can see that with a larger sample size, to get a sample mean that is less than 3, well, that 3.0 is really farther out on this X bar axis than it is on this X bar axis. Okay, and then the very last one. So now X bar, probability that X bar is greater than 2.4, same sample size of 25, so it's that same distribution as number 3. So now when you turn 2.4 into a z-score, so 2.4 minus 2.3 over the sigma sub X bar, you get 1.25 for the z-score. So a sample mean of 2.4 is in the same location as 1.25 on the z-axis. Okay, and then the probability that z is greater than 1.25 is 1 minus 0.8944, which is 0.1056. Remember, you do 1 minus on this one because you're shading to the right, because you're greater than 1.25. So we're shading to the right. Okay, the calculator functions are given here.